All right. Good morning,
Great.
everybody. Thank you for joining our webinar today on the 1510 Webster project. We have some guest speakers with us, Mike Baker and Michael Bauer, who will be talking about this project for you. As you know, I am the voice behind the webinars. My name is Chris. I'm the marketing for Rotoblast here. And I just want to, again, thank you for joining our webinar today. This one will be a great one, and I'll just let the mics take it over.
Great. Thank you, Chris. Today we want to focus in on 1510 Webster. It's a Type 4A project in Oakland, California. It's the first of its kind, especially in a high seismic zone. That's one of the challenges we had with this project. And I'm Michael Bauer. I'm with DCI, and I will let Mike Baker introduce himself.
Hi, I'm Mike Baker. I'm the Director of Architecture at OWOW. OWOW is a vertically integrated real estate company located in Oakland, California. And we have an in-house development, design, construction, and property management team. And our mission is to create sustainable urban living for the missing middle. So basically people making between 80% to 120% of the area median income. And increasingly, we're actually moving into the true affordable market. So, building really affordable housing for very low income people, primarily in the Bay Area, but we're looking to expand throughout California. The way we're doing that, the way that we're making housing more affordable is through innovation. So we're driving down costs through using innovative new construction technologies like prefabricated components, standardized units, supply chain management, and most importantly, an innovative mass timber structural system, which is what we're going to talk about today. Our goal at the end of the day is to build higher quality housing faster and at lower costs through innovation.
I also, too, real quick, want to just add, if anybody has any questions throughout this presentation, if you're on your computer, at the top bar, you'll see a Q&A section that you can click into and type some questions. And if you're on the phone, you should see 3 little dots at the bottom where you can go in and you can find that same section as well. And we will answer questions towards the end of the presentation.
Right. So I'll talk a little bit about why mass timber and explain how we're using it. So we're using it in a very particular way at OWOW, again, to help us meet our mission of driving down costs. So a lot of the things we're interested in with mass timber have to do with its material efficiency, its speed of erection. So basically, like we can kind of build a mass timber superstructure far quicker than we could with other traditional types of construction. That saves us money on our critical path, it saves us money on general conditions, and it speeds up everything around it. So it's a lot of that kind of scheduled gain is driven by prefabrication. So mass timber is kind of defined by its ability to be prefabricated. Everything is kind of CNC machined and milled off-site. It comes to the site like a kind of kit of parts and goes together really quickly. So that's really key to why we're using mass timber. I think the other big gain of using mass timber is it's sustainable. It has low embodied carbon, sequesters carbon, and based on the kind of suite of other technologies that go around mass timber, there's the potential for lower operational carbon over the lifetime of the building. And so based on all of these things, it's sort of efficiency, it's speed of erection. We are finding in our use case, it is cost effective, more cost effective than traditional construction types. You'll hear a lot of people saying it's more expensive, and yes, it can be expensive when it's used in certain ways, but the way we're using it, we found a way to make it cost effective.
And one thing I want to highlight with that, Mike, and you mentioned it, but I really want to emphasize is that you only use mass timber. All of your projects across the board take that approach, and I think that that's one of the keys to actually um, pushing, the amount of studies being done and whatnot, and getting projects to where they are today. So
Yeah,
I am good.
no, definitely. I mean, that's the other thing is we're trying to basically replicate our success. So learning from projects um, and taking what worked well to move on to the next project and to kind of repeat that and to always kind of be gaining efficiencies and economies of scale by using the same approach over and over.
And the scale of project that OWOW is focusing on isn't something that we could build out of stick framing. We're replacing projects that would generally be concrete construction, and so there's a lot to gain with all of those points: the sustainability features, the speed of construction, and so honing in on one specific construction type has allowed for a lot of exploration of efficiency. And it's been fun to get to work with OWOW. I'm Michael Bauer. I'm a senior project manager at DCI Engineers. I'm based out of our San Francisco office, which is, for those of you who aren't familiar, is just across the bay. I'm looking out now at Oakland, on the other side of the bay. I had the pleasure of living just a few blocks from the 1510 Webster project while it was in construction, so I was going out there almost every day just to check in on things, and it was an exciting project. I was really excited to be part of it. I've been at DCI for coming up on about 7 years now. We have expanded. We started in Seattle. We expanded across the West Coast, and then recently we've also merged with some companies on the East Coast, and so now we're spreading from coast to coast, and we've got licenses in all 50 states. So we're happy to work on projects in any state, and also Canada as well. We've got some licenses in Canada as well. So a lot of our mass timber projects are in the Pacific Northwest in the Bay Area, which is exciting because pretty much every engineer in our office has a mass timber project. But this is a project in particular, 1510 Webster is one that a lot of people wanted to take part in because it was exciting, because it was pushing the envelope on what we had done before, and because of some of the studies that got to go alongside it, whether um, it was for the mass timber front or just some of the challenges with getting things through a jurisdiction that was unfamiliar. It was definitely one of our more unique projects, and I'm very proud to have been a part of it. DCI is constantly trying to push a sustainability approach to design. Often sustainability can get misguided in thinking that we're going to drive up the cost. Our goal really with sustainability is to drive down the cost and provide a more sustainable option for our projects. So, if we can find ways of, thinning concrete slabs, that's great. But something that's really pushed the needle is switching to mass timber projects. Now that a lot of our builders around the Bay Area have comfort with it, we're able to pitch it on projects that, even life science projects that wouldn't traditionally go mass timber. And that's been really fun to be part of. There's still a lot to learn about mass timber. And so it's one of the biggest shifts that the structural engineering industry has had. And it's great to work for a company that really is pushing the envelope on that. So we are part of SE 2050, and we do have a sustainability team in-house that is capable of running the LCAs and doing a lot of the ECAP planning, the sustainability analysis on projects to be able to figure out where we were efficient and potentially where we can be more efficient on our future projects. So, quick overview of what we're going to present today. We're going to start off just talking about mass timber framing systems, which some of you may already know, but we want to just highlight what options are out there. And then we're going to talk about the evolution of OWOW. And by that, we're really going to look at kind of a case study of an initial project, which was more of a lab, and then how we got to 1510 Webster, and how we made that transition. That's going to include a little discussion on some of the lab testing that was done. Then we're going to review 1510 Webster as a case study and really hone in on those mass timber connections, talk about a few key lessons learned, and really we want to open this up as a Q&A. So if you have questions, go ahead and post those, and we'll get to those at the end. So mass timber framing systems, I think this graphic's great because it shows the two key ones that we're going to focus on today. There is also the bearing wall timber framing solution. As I mentioned earlier, it doesn't really fit into the place of what we're talking about by replacing or adding new construction types. We're not, if we're using light gauge walls, we're not changing quite as much. So the ones we really want to focus in on are going to be the post and beam, which is kind of more conventional. It's a one-way panel span to beams, and the beams are supported by columns. Now, you can also use a girder system and have post, beam, and girder. We do get nice open spaces. So if you were going to do either a classroom or a larger space, you can get really impressive spans and spaces out of that. The downside for us is going to be that it's going to increase the depth of these elements, and we're going to add a lot of additional connections as well. So there's a time and a place for it, but today we're really going to focus in on the point supported or the post and plate. The post and plate is going to reduce spans, but it's going to increase the clear height. And the key difference that at least I found was great was it was very easy to coordinate with the MEP consultants on these projects because there's nothing to interfere. It's a lot more similar to a flat plate concrete project than it is a typical mass timber project. We're not talking about making horizontal cores. And then where we are making vertical cores, our tributary load to these columns is relatively low. So we do have some flexibility with locating plumbing penetrations along the panel. And that's something that we coordinated. We ran modeling analysis on to be able to develop where we were able to do those. But one of the key things on that, and I'll pass it off to Mike for this, is OWOW took the lead on this project, and they knew one of the best ways to find efficiency was going to be to run some tests. So I'll pass it off to Mike, and we'll talk about 12th Street, and then we'll go into some of that testing.
Thanks, Michael. A few years ago, while 1510 Webster was kind of in its planning and development phases, we built another small mass timber project here in Oakland at 316 12th Street. It's a mixed-use building, 2 stories of commercial with 3 stories of residential above. And the way it had originally been conceived, if you look at the picture on the left, is as a kind of post and beam or post beam and girder kind of structural system. So the bottom 2 floors were actually built in this fashion, it's really beautiful. The timber is from Austria. It's a really nice looking commercial space, but we realized that it wasn't going to be a good solution for building affordable housing based on its costs, based on the complications of coordinating all the mechanical through those beams, the depths of the beams that we were going to require. It just didn't make a lot of sense. And so we saw this project up in Vancouver at the University of British Columbia called Brock Commons. I'm sure many of you may be familiar with it. And it utilized a point-supported or post and plate approach. And we saw what they had done and realized it could be the perfect fit for our approach. That project was for student housing, and the sizes of our units and the structural bays were pretty similar. So we decided kind of midstream through this project to switch our structural approach and to build the 3 stories as post and plate instead of kind of post and beam. And we kind of, we took inspiration from that Brock Commons project. We based a lot of the kind of the spans and the kind of structural column spacing and the sort of column to column details off of sort of the best known available evidence at the time, the testing data that could support those spans. So it was a pretty tight column grid, probably about 12 feet by 10 feet, something like that. And it was also based off of the capabilities of the materials. So we were looking at CLT. We were going to buy our CLT from Katerra. at the last minute, Katera went bankrupt, and we had to pivot to another material suddenly. And so in came Ferrer's Lumber Company up in Oregon, and they built something called mass plywood panel. And it's basically like a giant thick sheet of plywood, 5, 6, 7 inches thick, and anywhere from 12 feet wide to almost 50 feet long. And the price worked for us, the lead time worked for us, and so we pivoted to this mass plywood for the floor panels. So what you're looking at in these pictures here, the columns are actually the similar product. It's called mass plywood laminate, MPL, and the floor panels are mass plywood. And we based all of these spans and spaces off of kind of the existing tabular data for CLT. But as we were working with it, we realized that it felt significantly stiffer than the CLT we were used to dealing with. It had really great properties. It seemed really, really stable and strong. And we decided we want to use this product for 1510 Webster, which was in development at the time, and we want to take it to its limits. And so that's where we brought in testing. So Michael, if you go to the next slide.
One thing I want to highlight real quick is if we just take a quick look at some of the connections here. This was, to Mike's point, what the standard connection of these custom built up connections are. And you'll see just the long way that we've come from where the engineering team, that project wasn't by DCI, but we had something proposed that was similar for 1510 Webster, and then we'll get to the connections in a bit. That's just the one graphic we have to kind of look at how far we've come.
Yeah, so we commissioned Wood Research and Design up in Oregon to run a bunch of structural tests, and Michael can probably speak more specifically to the tests, but in particular, because this is a point-supported approach, we needed more data on the punching shear capacity of the panels in particular. So we ran through a whole host of tests, and unsurprisingly, the panels performed significantly better than we had originally kind of anticipated. I think we basically broke the testing rig at like 130,000 pounds.
We couldn't force the punching failure. And there's been some other tests since then. They've had similar results. But the punching failure often causes a flexural failure. So we're still getting that bottom lamella at the point of load application, which is great because punching failure is a brittle failure and we're trying to avoid it. But it was hard to get any data that we could kind of back out after that because it was so strong that it was forcing the limits. You can see the beam above at the very top of that image here is actually bending a ton, and they were worried about breaking the rigging equipment, not the panel. So the panel was stiff, but it also was meeting the deflection limits that we were looking for. So the testing went really well.
Yeah, and those were the key tests. Additionally, we were looking at fire testing and also vibration testing because vibration is kind of one of the key drivers for mass timber projects. It's mainly an occupant comfort kind of. You don't want people to be walking around on bouncy floors. And again, the kind of stiffness of those panels helped us to reduce vibration. I think in terms of the char, I mean, we can talk a little bit about the kind of key operative behind mass timber is that it chars. And so in a fire event, the outer layers protect the rest of the wood fibers from, they char and they protect the wood fibers and give the wood a kind of inherent fire rating. And so we were able to really aggressively reduce the panel thickness based on its strength down to 5 inches from, I think it had started initially at 7 inches when we were looking at the project, down to 6, down to 5. And it helped us to increase our column spacing from 12 feet to almost 16 feet in some places, which really helped our unit layouts. And it also really helped us achieve efficiencies on the project because we were able to remove literally hundreds of columns from the project and that's hundreds of columns that take time to install, that have connections, that, you know, that influence the kind of design of the spaces. So it was really transformative for the Webster project, having done this testing. So this is 1510 Webster. You've probably heard of it. It's a 19-story project here in Oakland. It's multifamily residential with 236 dwelling units and 186,000 square feet. It has a 2-story type 1A podium, so it's post-tension concrete. And then above that, we have 17 stories of type 4A. 16 of those are mass timber, and the kind of roof penthouse is cold form steel. So this was the first prescriptive type 4A project in the country. And by that, we mean it's complying kind of as of right with the 4A building code. Here in California, unfortunately, we can only do 17 stories of mass timber as opposed to the rest of the country. But otherwise, it's compliant with the code. And a big aspect of that is everything needs to be encapsulated. It has a 3-hour rating. It's a really robust structure. The codes are pretty conservative, but even then, we found great success with the erection of the superstructure and the enclosure. So we were able to go from the top of the podium. So it took us a couple of months to get the foundation and the podium in place. Once we had the podium in place, we basically built this entire building, superstructure and skin, in 2 months. And this was a real testament to the benefits of prefabrication, the benefits that mass timber can bring when it's executed with that speed and with that efficiency in mind. So here's a quick video. It's a little truncated, but it gives you the idea. We're basically doing a floor every, I think, between 3 and 4 days. We would set the mass timber columns for a floor in a few hours, literally. We could set an entire kind of floor panels in less than a day. And so we're using a prefabricated facade system that comes in large 30 by 10 foot sections that literally clip onto the building, and we could do an entire floor of those in a day. So it was really, really insane how quick it was going. We could barely keep up. But we'll talk a little bit about what made that possible in the next couple of slides.
One thing I wanted to add there is I think that you could probably tell from the graphic, but the mass timber structure of 16 levels of mass timber seemed to go up just about as fast as this penthouse for the elevator overrun. Everyone knows elevators are challenging, but it really did. I think that we had more headaches about trying to get things compliant with the elevator shaft than we did with the number of RFIs that came in during the timber installation was just a handful, and they were pretty easy to respond to as well. So it was really smooth on our front, and you can also kind of see from the image how few people are on site. So I just want to emphasize how smoothly the project went from our perspective.
Yeah. So the superstructure was erected by Webster Timber. So they're the concrete. Webster is a concrete contractor. So they did the core. There's one concrete core and one shear wall, and they had a lot of experience in flying forms for concrete, and so they had never erected a mass timber project before, but they said, hey, this is pretty similar to what we do in concrete. Let's give it a shot. So the erector had no experience with mass timber, and yet we were still able to figure it out and excel at it. Same thing with the facade. The erectors were local framers that we'd worked with that had no experience in kind of maneuvering or connecting these large facade panels, and yet they were able, after the first day, to install a panel in less than 15 minutes. So it's pretty awesome.
Well, while we're here, one other thing to kind of note is that OSHA does have requirements on the code, and OSHA have requirements on how much exposed mass timber. So you'll often see, we had a project on Treasure Island, and the project had topped out and they hadn't set the first facade panel yet, which obviously isn't great from a moisture protection plan. This is in the code because of fire protection plan, but there is a limitation on how many levels of exposed timber you can have at a given time. And so that facade has to chase the high operable deck. And that's something that means you've got to have a lot of coordination. You can't have something lag. These panels were coming from Canada, and so they had to get to site on time. They're coming off the truck and then being installed in order to be able to release the next level. And so that first level was a little bit slower. I want to say the first level, the panel still went in a single day, but from first to second level of timber was what, 4 or 5 days. And then that repetition got all the way down to 3. And then the last couple levels, once the core had topped out, they were setting those in 2 days, like a day for columns and a day for panels. And it felt like they were finishing placing the columns by noon and the panels by like 1 or 2 p.m. So even with all these working days, there was constantly crane utilization. They were constantly doing something. But it also was super efficient at just trying to make sure that the next thing was going in place. So if they were having some issues with a column, they could pivot and be able to tackle something else. So kudos to the OWOW construction team and the Webport construction team for having that plan in place and really being able to take full utilization of the crane.
All right, let's go on to the next one. So again, we'll kind of fly through some of these, I think, so that Michael has some more time to speak about the connectors in detail. But here's a photo of it under construction, showing the kind of sequencing where we've got the story of the timber column set. We've got the floor panel below that, and another thing that Michael didn't mention is we had to follow the mass timber with the encapsulation, with at least one layer of encapsulation. Same as the facade. We couldn't be more than, I think, 4 stories above the active or below the active level of highest level of construction, mass timber. So there needed to be a really tight coordination for running through that sequence and keeping up with the project.
And we also couldn't be too far above with the core itself. So you had limitations on core height and how far the concrete could go based on, ladder reach, and then fire protection, like Mike's saying, with both gyp and facade. So there were a lot of moving pieces.
So here's us setting the first floor of columns, and so this is sitting on top of the concrete podium, and you can see there those are the roseblast pillar connections that Michael will talk about a little bit later, but they were pretty pivotal in helping us achieve the speed of erection that we did, because basically the connections arrived on site maybe a few weeks before, and our team on the site basically installed all the connectors to the bottoms of the columns on site, and they sort of set up in a little assembly line. I think we have a photo of that later. And then the columns were lifted in bundles onto the floors. And then, actually, no, they weren't lifted in bundle. I think they were just placed individually by the crane. The tower crane was picking them because they were pretty heavy. So you see here that the top stat, I think we were able to place columns in 3 minutes per column with these connectors, because there's only a few fasteners that needed to be made on site. And they're braced, but they were practically self-supporting. They could kind of stand up, and obviously they need to be braced before the next layer of flooring comes on top, and the bracing also helps us true them so that they're long. And here's the last MPP floor panel flying in, or one of the last. I think it's the second to last.
Also one of the smallest.
One of the smallest, and this is about 2 months later. You can see how few crew members there are actually on the active level of construction. It looks like maybe there's 2 guys actually installing the panel at the moment, and the other ones that you see are actually it looks like they're installing splines or, kind of between the other MPP panels that are installed. So, there's a tower crane operator. There's probably 1 or 2 guys down on the truck where they're picked straight off the truck, and then a few on the active floor. So it was a really lean team, and everything just kind of slots in place. That's the power of prefabrication. It's super precise. Everything is CNC milled with the right tolerances, and I think across the project, our tolerances were less than 1/8 of an inch, kind of across the entire length of the project.
With the exception of the concrete, I think that you're right.
Yeah. So here's what I was just talking about. All of this is built in a kind of digital twin environment and in the digital space to a really high degree of fidelity. And so that means every plumbing penetration, every HVAC shaft, every connection, literally every screw is modeled in the digital space so that we can find all those problems before we get to site. And then these panels are fabricated directly from that digital twin. So all the plumbing penetrations are already in place when we get to site. Obviously we can go in and drill some after if we need to, which we did. But having a lot of that work done beforehand saves us a ton of time on site. And here's a kind of closer look at that process, which included not only kind of the modeling of the physical elements themselves, but a kind of modeling of how workers could actually install those components, how they could reach into tight spaces to fasten nuts and bolts. And we ended up having to change some of our details to actually accommodate constructability.
Yeah, it's pretty easy to draw some of these details and think that it'll work, but then actually working through hand access and tolerance, just for me, it's easy to think, okay, well, I can call out an 8-inch wide by 1/2-inch plate, but that thing's 30 feet long. That thing's hundreds of pounds and incredibly hard to move. And so we had we really had to think through what it was going to be like on site and what was going to be restrictive and what would give us some tolerance. And so working with the clash detection team and OWOW to be able to figure out what was going to work was imperative to the speed of construction that we saw on site.
This is a shout out to CAD makers. They're also up in Canada. They were instrumental to getting this project built. And here's another view of the mass timber panels, and what I was explaining before. They're literally coming off the truck. We were lucky enough to have a staging kind of yard directly adjacent to the site, but most of the time we were able to just take all the kind of panels right off the truck because we actually didn't want to have to double handle them. You don't want to take them off the truck, put them in a pile, and then pick them up again because they're actually in order. They're coming off the truck. They're stacked in the right order so that the whole the flow of everything is uninterrupted. And again, you can see how few workers. They messed it up, but we figured it out.
They had the training wheels on for the first few levels, and there were some times where they'd place them down. I think that they probably had a different panel sequence of putting it in forwards and then backwards. They had a number of different sequences where there was one panel that didn't come off quite right, and so the number of different ways that they were able to move and install it was pretty fun.
Then just a quick discussion on encapsulation. Because this is 4A, we have to achieve a 3-hour fire rating. So only 1 hour of the fire rating is able to come from the mass timber elements. The rest has to be provided by non-combustible encapsulation, which basically means wrapping everything in 3 layers type X drywall. So this hits our. It's a shame because the wood is beautiful to look at, and it's a shame because this impacts the sustainability of the project. That gypsum board, has a pretty high carbon footprint, and so we're definitely looking at ways in future projects, especially in the 4B type, which is basically up to around 12 stories, where the upcoming code cycle, it's going to allow full exposure of the ceilings, which will mean that we're going to have to provide kind of maybe a thicker floor panel, but we're not going to have to encapsulate it, which we think is going to be pretty instrumental in getting kind of more widespread adoption of mass timber. And then just to speak briefly on some of the other things we have to do. So we have to also provide a non-combustible topping, which typically in mass timber is gypcrete, and that also serves double duty as an acoustic. It has acoustic properties, so we've got some Acoustamats and some kind of flooring underlayment up there in addition to the gypcrete that help to mitigate the kind of impact noise. The mass timber generally performs really well from a STC perspective, but IIC impact noise is kind of a big deal, especially in multifamily residential. And we're kind of able to hit the code minimums for our product, but for kind of higher end housing, you're probably going to have to use a more kind of substantial floor buildup to achieve higher IIC ratings.
Now we're going to jump back into the connections, and I think this is a really cool picture because you can see those Rotoblast pillar connections being installed with the panel right here. So the pillar connection was not the initial plan for the project. We went through a number of iterations. You saw the 12th Street connection, which was an oversized plate. We had something similar to that. I would come back to us and they'd say, we've got some ideas. What do you guys think about trying to do something where we install it and we can kind of fasten it as we go? And so we'd come up with some details that were kind of our own three-pillar connection version of that, where we were looking at something a little bit more isolated, fitting within. One of the concerns with the 12th Street is in type 4A, but our concern was the fire protection of those panels. And so then finally, I think again came back to us and said, well, we've got this really slick connection. It's coming out of Europe. And we'd like to study the feasibility for the project. And we saw it and we met with the Rotoblast team. We were really excited because it was managing all of the things that we were looking for. It had the strength. It had the quick installation. And one of the other key things from the structural perspective is that it really is acting as a true pin here. So in our column connectors, we don't want a lot of rigidity of those columns. We want the shear walls to be taking our seismic loads, and we want to be able to create less fixity at the columns themselves. So if there's some rotation there, we can handle all of the lateral resistance for the shear walls and allow these to rotate. And the pillar design really perfected that. We were able to work with the Rotoblast team to kind of customize these for our seismic conditions, which was challenging. And I think that, in some cases, we took a conservative approach with, making some screws a little bit longer to be able to verify that we were going to have the resistance. But those are, that's a small price to pay, a couple extra inches of embedded screw to be able to meet the seismic demands of California right near the San Andreas Fault and still maintain something that could be installed in just a matter of minutes. So you're seeing the deconstructed column is pretty interesting. The screws are going to go into it's basically built out top and bottom on the ground. And one of the things that we did is we selected pillar connections that were uniform for an entire level. So all of level 5 would have the same connector as would all of level 17, but those two pillar connections were going to be quite a bit different because up at 17, we were going to have substantially less load. So we were going to have thinner plates we weren't going to have the same screw embedment. So we were able to customize them by floor, but that also made those columns interchangeable, because as you change plate thickness, you need to adjust your column length, your cut length for them. And so we are keeping columns all consistent amongst entire level, and the connections consistent amongst a level. And that includes, you're seeing a corner column right here, and that's going to be the same as a interior column as well. So we're kind of enveloping worst case, but still able to find some efficiency by reducing the plate thickness as we went up the building. So here we've got some installation images. They were all fabricated on the ground. And again, all these columns are the same because they're all for one given level. So they're fabricated on the ground and then lifted into place. And then they were able to place them with a crane and basically thread the bolts through and get the nut on to be able to stabilize the column. Those were snug tight and they would hold in place. If you twisted it, you could get a little bit of twist out of it because there was a slot, but they were stable, and then they would come back and plumb them and get them square with those braces, and then they would get restrained again by that top plate connection as well. So it was a really slick connection. It was far faster than what we were reviewing with the OWOW and their web core team with any of the details that we had come up with. It's a really well thought through connection. It's strong. So we were really excited to be able to incorporate this on the project. And I've got to give kudos to the Rotoboss team, because they worked with our engineering team. They developed calculations to be able to justify seismic drift compatibility. And so it was really pivotal. And again, this was a late implementation. We had already submitted for permit at least once with the city of Oakland, and Bay Area jurisdictions for permitting are not easy. They're very challenging. Among our company, they're probably some of the most challenging. And Rotoboss was able to get that in, and we were just able to submit it. We didn't get any comments because it was a very robust calculations package that we had coordinated with them. We didn't really get any comments on the pillar connection whatsoever, which is a testament more to the upfront work that was provided by Rotoboss on that. So it was a big success for us. We were excited to be able to use it, and we're certainly looking to use it on future projects. So then just to look at some of the other efficient connectors, if our Rotoboss connectors go in just a few minutes, we've got to be able to install the other connectors at a similar pace and find additional efficiency. So one of them I want to highlight is the core connection I mentioned earlier, and Mike had mentioned that the tolerance was really tight on the project, probably less than an eighth of an inch, basically everywhere. It was a very close approximation to what we were seeing in the computer, but the core was the one thing that we didn't have a ton of control over. And the construction team informed us that they needed a little over an inch of tolerance. But then they told us that that inch of tolerance could go in either direction. So it could be an inch in or an inch out. So really, we were planning on 2 inches of tolerance there. And the core connections that we were originally using were going to be challenging to get that as a reliable connection without field modifications. One of the more traditional connections for a concrete core is a L angle with the leg down and then welded to a series of embed plates. Those are generally at like 24 to 36 inches on center. So a lot of embed plates, continuous, big, heavy, continuous angle. But if you're looking for that tolerance, and if the wall is going in, then the panel's not getting the same bearing area. And then finally, the last challenge with that is that you're going to be screwing from the underside up for all of those fasteners. And we're talking thousands of fasteners per level. So, tens of thousands of fasteners along the project would need to be screwed from the underside up, which is going to start impacting the critical path on the levels below. So DCI came up with a connection that was going to be able to accommodate tolerance. It was going to bring all of those fasteners to the top side, and it was going to keep up with the speed of installation that we needed. So we didn't really see we didn't see any setbacks from this, and that was one of the big successes. We also implemented prefab spline connections as opposed to what you're traditionally going to see, or what we used to see was a plywood spline that reduced CNC time and it increases strength. Those spline connectors are a lot stronger than what we're seeing with a plywood spline or diagonal screws. And then lastly, we had a what we're calling the double duty cords. We need that edge of diaphragm restraint for bending. So as the building's moving, we see tension and compression at the extreme fibers at the edges of the building. So what we did was we created a continuous cord element for that tension force, but we also were able to utilize the vertical leg of that to hang the curtain wall. So that kind of fed right into the speed of installation of the curtain wall. And we previously mentioned that's on the critical path for the encapsulation. So we really had come up with, I think each of these had a number of different iterations of where we were. And we found ways of customizing these and getting them so that they could keep up with the speed of installation. And the result was 1510 Webster. It's now for lease, and it's been a big success for us. And now I think that we're ready. Mike, do you have anything you want to add before we go to Q&A?
I think there was one more slide with some conclusions.
That's right.
Yeah, so I think, some of the key lessons learned from this project were that the mass timber structural system brought a lot of benefits, but it did require a significant upfront investment of time and money to plan it properly. We talked about the extensive VDC process. You also have to consider the material lead times and the money it's going to take to kind of upfront those prefabricated long lead time items before the project starts. So I think the mass timber was relatively quick lead times, probably a few months. For example, the prefabricated facades, you're looking at 10 months to a year from the time that you sign a contract to the time that the first panel arrives on site. So something definitely to keep in mind when you're looking at mass timber projects. It was super fast and it beat all of our estimates. It blew them out of the water, which was amazing. And yet the kind of ultimate lesson was that you're only as fast as the slowest thing, right? You're only as fast as your critical path. So the rest of this project, what you're not seeing here was built mostly with on-site labor. So, traditional metal stud framing, all the plumbing, all the MEPS, everything was built on site. And those things were subject to the same kinds of delays that we see all the time in construction. And so our ultimate lesson learned for WOW is how do we get more aspects of the project prefabricated? How do we build more of it in the digital space to this really high degree of resolution and get it built in a factory and brought to the site and just plugged in? Because what we saw was a total validation of this approach and the kind of the ways that it really beats traditional ways of building. So we're actively pursuing how do we bring this to every aspect of our projects.
Great. I think that brings us to our Q&A. Mike, do you see if there are any? I'm still sharing, so I'm not seeing any.
Yeah, there's one. So the question was, what kind of machining tolerances do you use on the panels, and would you make adjustments if you were again? I think the tolerances were like 16th or 32nd for machining. They were really, really tight. I don't know if Michael, if you have more information on that.
Yeah, I mean, I think they're tighter than a 16th because we were watching some of the interior panels, particularly these ones at the corners where you've got the routed hole coming over the top, watching those panels get installed. Things were really precise. I wouldn't change much on the project. I certainly wouldn't be tinkering with that in particular.
Yeah, I mean, that's one of the key qualities of mass timber is the kind of precision with which it can be manufactured is it's really high because it's straight from the digital space. So the tolerances can be really low. You know, you're pretty much just considering like, okay, um, what are the installation tolerances mostly, and not the actual physical properties of the material.
Well, and that's a good point. I think that we had thought through a lot of ways to adjust. So, for instance, let's say a column were cut, a 16th or even an eighth of an inch short, um, which usually wouldn't be the case. More likely than not, you would have a concrete column somewhere along the slab that was, lower by that margin, because we do have a transfer slab, so you do get a little bit of deflection there. So if you've got something low, we had ways of being able to use spacer plates, and this is something that Rotoblast provided, and they were seldom used because it just wasn't necessary. But there are spacer plates to be able to make up that vertical tolerance, and we had a number of ways of trying to address or realign things if we did get askew. And we were constantly taking surveying analysis on the project to be able to verify that things were in place to where we wanted them to be.
I have a couple of new questions. So the first one is, did you think about installing the column connection in the shop versus the field? Michael, do you have context on that?
Yes, there was interest in it, but then you got to ship them up to Freris. One of the benefits of being able to do it on site was everything could get to the site as quick as possible, and Webcore was able to monitor and be able, their timber team was able to monitor and be able to install those all in one place. If you didn't have the laydown area, it would still be possible. We've been looking at doing this on a number of other projects where you can do it somewhere inside, in a relatively small amount of space. They go together pretty quick. So, you could install them in one day or you could install the connections to the columns one day and then place them the next day pretty seamlessly, even for a pretty large floor plate. But the reason we did it was just trying to get everything to site as quick as possible. As we talked about earlier, the Rotoblast connectors were a late implementation and one we're glad we made.
Yeah, I think getting everything to site, I mean, the logistics is really challenging, especially when you have things coming from multiple continents. And so, yeah, I think as Michael mentioned, the less movement that we had to do of parts kind of across borders and up and down the west coast of the US, the better, because that shipping also adds time and potential costs. Another question, the 72.4 million was structural cost or total for the 236 units? It was total. I think the cost has probably crept up as we close out the project. Our original target and kind of original contract was slightly over 400, and it's probably up around $420 a square foot. It's just the way things happen. There are unexpected cost overruns. But when compared to a comparable concrete building, you're looking in the Bay Area at around $600 a square foot. So it's still significantly cheaper. And I would say, probably about 20 to 30% of our savings is coming from kind of mass timber and envelope. The rest of it is coming from a whole host of other strategies, in terms of supply chain, sourcing, really diving into kind of efficiencies. A lot of it is in the kind of MEPS system as well. There's another question here. The 3 layers of gyprock for fire protection was a cost-effective or structural design decision? It was, I would say we wanted this project to be a prescriptive project. We didn't want to go through a long kind of review process with the city with an alternate means request, because we certainly could have exposed mass timber, but it no longer would have been a prescriptive project. And so we decided we wanted to comply with the code, and the way the code is written, it basically it requires 3 layers of 5/8 inch type X gypsum. So I guess at the end of the day, it was a cost-effective decision because it helped us save time on the project with the review process, and it enabled us to use thinner mass plywood panels, so the volume of wood in the project was less. If Michael, you have anything to add on that?
Yeah, just to quickly add to that, we're doing analysis for the in-place panels, and then we're also doing analysis for those panels with slightly different criteria with that char layer. So we kind of have to work backwards from that second test on what the allowable panel is with the char layer, and then start adding to that. So if we were to add 2 additional hours of char, we'd be adding, over 3 inches of additional panel. And so you'd be looking at a 7 or an 8 inch panel, which that is substantially more expensive than the 5 inch panel. How that compares with the labor associated with the chip layers, we have been studying that. But to Mike's point, just trying to make sure that we were able to get this project built in the city of Oakland in their review process and meet that 4A requirement. It was a pretty easy decision on this one because of the height of the building to provide that chip protection.
Yeah, I think in certain markets, especially luxury housing, having that exposed mass timber is a real value add to the project. And so the additional cost of more timber, maybe the additional cost of the added review time makes sense. But for us, it didn't make sense.
And we're also seeing the code, even in the time that this project started before the adoption of the new modifications to type 4. Those were adopted, the project was permitted and built. But even since then, we've seen changes to the code. Originally, we were highly restricted on our type 4B exposed mass timber, and the code is making provisions now and in the upcoming code to be able to allow for those to be exposed. So I think that it'll follow. I think that we need more data. I think that we need to get more jurisdictions comfortable with the fire rating and have a better understanding of what char is, and that we've engineered this. So in time, I think that it'll be more viable to have high rise with exposed mass timber.
I think I got one more. I think we have time for maybe one more question. What approach did you take from a moisture mitigation standpoint? So we're very lucky here in Oakland in that basically from around April 15th through November 15th, it doesn't rain at all, period. So you might have seen in one of the pictures when we were setting our first layer of columns, we did get like the last rainstorm of the year. But after that, it didn't rain. So we didn't really have a moisture. Sorry, I misread the question. Is moisture migration? I don't know if it meant mitigation, but we didn't have any real mitigation activity. In terms of migration, I'm not entirely sure. If there were water that kind of got onto the timber during construction, it needs to dry out, and so it needs to sit in the sun for a couple of days. But I don't really have a good insight into that.
Yeah, we didn't really have. I went to the site very frequently, as did you, Mike, and we really didn't have standing water on the panels themselves. It is funny because the last concrete level does show the rain, and we would have had more rain had the concrete levels, the basement level, particularly the foundation, not had so much rain that year, because it pushed we were a little late on getting the timber going because it just rained so much around New Year's of that year. And I remember it just being super muddy. And I had another project where they kept delaying the concrete foundation pour. Finally, they worked with the site and they were able to do it, and it timed out to where columns were set. We got our last rain, and I don't remember it raining a single time after that. So there's a little bit of, sometimes in the morning you'd have that morning dew come in, and things would get a little bit wet, but then as things would dry out, they would make sure that things were dry and hitting and we're not having high moisture content prior to encapsulating them.
I think we're at our time. There's one more question, but Chris, I don't know if we have time to take this one or not. I can go ahead. It's what's missing in general in the industry for hybrid construction. Not entirely sure. So by hybrid, do you mean a mix of construction types? So like mix of steel and wood, or concrete and wood, or
different office and residential. I guess one
yeah,
thing to note on the timber to wood that I just want to add real quick is we could not use a timber solution for our lateral system on this project because of our seismicity. There are code restrictions that we weren't going to be able to do it. Also, just feasibility of being able to do to withstand the forces that were generated. We basically got to choose from concrete and steel, and we liked that the concrete was going to be able to be done by the same team that was going to be able to install the timber. So it worked really well with the concrete team, basically just jumping from building the core to the timber. As for whether or not we need to do podium levels and for those vertical levels of concrete, I would love to do these projects and find ways of avoiding the concrete, at least for a good portion of it, and stacking that timber all the way down. Because one of the biggest challenges is in the slowest level that we had to place was that transfer deck. So the more efficient you can get with your transfer systems and the more timber you can integrate into the project, I think the more successful you'll be.
agreed. One more question. This is from Malesio. I know he's a plant. I think he works for the boss. How can you make sure that the concrete is cured enough with the speed of construction? We fix the bracing to the core even with only a few days of curing. It's for you, Michael.
Well, they're actually flying that up several levels, and they've got an early high mix in there. So we were getting testing data back on the core. The core was an 8,000 mix. To be able to fly the core, they were still looking to hit, at least 4,000 or 5,000. That's something that the actual lifting of the core was something that WebCore was managing with their engineering department. But as for actually making structural attachments to it, we were looking for 75% of the concrete strength to be able to set that, and it just happened to work out. They were working about 3 levels above it. 3 levels takes 9 working days, which was about 2 weeks, and they weren't having any issue within 2 weeks of hitting 6,000 with the early high mixes.
All right. Thank you, Michael. So that's all the questions.
Great.
Is our moderator still here?
He did
So, Chris is currently in a car, so I'm going to speak for a second only. Thank you guys for the presentation. It was really interesting. I hope also everyone watching liked it. And yeah, if someone still has questions, you can write us under the marketing email of Rotoblast. Just send us a question and we will try to answer it. And otherwise, we hope to see you next week for the behavior of self-taping screws in glulam under moisture change content webinar at 11 a.m. on Wednesday again. Thank you.
Great. Thank you, everyone.
Great. Thank you. Good job.
Thanks, Mike.
Bye.